All right, everybody online can hear me okay?
Yes, sir.
Let's see, this is not 450, 548. All right, and homework was to write some assembly pseudocode, let's say, something like that, that kind of operates with this this idea. So you would load some numbers into 3 variables, and then reverse those variables in memory. So if initially var1 was a 1, var2 was a 2, var3 was a 3, if that's your starting state, then we want in the end var1 to actually hold the 3, var2 to actually hold the 2, var1 to actually hold the 1. How'd that go?
Very good. I have very good.
Good. You have a question?
Yes.
Okay, what's your question?
About the code posted here, which is posted on the
Screen before, or 2 screens before?
Yeah.
Okay.
I have a problem with this code. So I know you said that we should send our code in text file, but I already tried the code in the Azure website.
Yep, right, yeah.
And so I had to troubleshoot a bunch of stuff to understand this code. And I have a small problem with it, and I need you just to explain this bit for me. So I'm gonna quickly dissect this code based on my understanding yesterday and the day before that variables and the dot word is just similar to like identifying an integer or a float.
Yeah, it's a type.
Yeah, it's
Yep.
a type in other programming languages. Now,
This is 4 bytes. A word is a 4 byte value.
4 or 2. It's 2 bytes.
2 bytes, 2 bytes.
So yeah, so I was looking at this yesterday. Anyways, that's what I have a problem with. Now, the Azarea did not actually accept the word type for the numbers, and I don't know why, but this is not my code has the dot word.
Sure.
But when I tried to emulate it in the Azarea,
Right.
It only accepted a dot byte. Did not accept a dot word for the number. I mean, not for any.
Gotcha. For the type value here,
Yeah.
it didn't accept that word.
Yeah.
Okay, I'm not sure why. It could have been. Actually, I have a guess. We haven't talked about it because I wanted to focus on ARM, but there's like a competitor language. It's not competitor. It's related to the same thing. It's called Thumb. Get it? ARM, Thumb. Okay, so Thumb is a almost like a miniaturized version of ARM for even like smaller embedded computers and things like that. So I wonder if the assembler you were using on there, I don't know, I haven't used their assembler, but there might be a switch that goes between Thumb and ARM. And it's possible that, because Thumb definitely doesn't allow as large of data types, it's possible that's why. It's also possible that they just haven't fully supported stuff. It's probably in like alpha something or other, where it's just like, look, this works for bytes, so you can kind of get an idea for it, but anything bigger than that, we haven't implemented. So that's also possible, if not more probable.
Okay, but that's not my big problem, because this is a programming kind of question. But I have a question related to our course.
Okay.
Now, a word is, as we said, is 2 bytes.
Mm-hmm.
Okay, and I'm storing number 3. 3 is actually 2 bits. Technically, it's 2 set bits. If
the smallest representation of 3 can be done in 2 bits.
Okay.
But this is a 16-bit version of 3.
Well,
which will be 14 zeros followed by a 1 1.
That's the point I want. Yes, exactly. That's the point I wanted to understand. Am I wasting the remainder of the register by just storing a 3 there? It's so I'm putting a type, a word, which I'm assigning a 16-bit to the 3. So am I wasting 16 bits from the 32-bit register just for this number, or does the register delete the remainder of zeros, or use them, sorry, not delete, use them for something else?
It won't automatically use them. So for those of you online, because I know you probably, it's hard to hear the conversations in here, but you know, his question was related to like this first thing here. There's var1 word 3. So if I come in here, so if I say var1, what is it, just dot word 3, something like that. This is the same thing as like in C, since a word is 2 bytes, that's 16 bits, it would be the same thing as saying short var1 is equal to 3. That's like the in C, all right, because a short data type is a 16-bit value. A char is an 8-bit value, and int is a 32-bit value. Okay, so these two lines are kind of equivalent. So his question here was, are we wasting space in the, we haven't actually put it in a register yet, but we will put it in the register.
Yeah.
So the thing is when we, what did they do it as a load, or do they do it as a move? Okay, yeah, so they load into R0 the address of var1, and then they load into R2 the actual value that lives at R0. So your real question here is are we wasting space in R2?
Yes, in the register.
Yeah, well, specifically R2. So just walking through this real quick though, notice, let me just get everybody on the same page so we know what the code is doing, because it's a good question. All right, so we've defined a couple of variables up here, right? var1, var2, var1's equal to 3, var2 is equal to 4. We've advertised these guys as being 16-bit values, okay? Because that's what a word is. A double word is a 32-bit value. A byte is an 8-bit value. All right, so now here's where our program actually starts. So what we do first is we load into register R0 the address where var1 lives, which is done down here.
Right.
That's where we're getting those values. So R0 actually holds a memory address. R2, when I load into R2, I'm giving it the value that lives at that memory address. So in this particular code here, R2 holds R3.
Okay.
That make sense?
Yeah.
Okay. And similarly, we're loading into R1 the address of R2, and then we are actually we're storing into R2 the value of we're actually overwriting it. We're not storing into R2. We're overwriting a place in memory with the value that lives in R2. So we're overwriting var2 with the 3. All right. But for your question, let's focus on the first part. So the first part, he said he's not really concerned about this line. This line is just the gateway drug to this line. All right, so R0 gets the address of R1, and then R2 gets the value that lives in that address. Great. So after this line, R2 is equal to a 3. Now R2 is a 32-bit register. So if we go into here, and I'll just put we'll say load, was it load register like that, LDR? R2 and then the address of R0, and this is after we loaded into a register R0 the address of var1. So here we'll just put a little comment in here. This loads the address where a variable lives, or where var1 lives. This loads the actual value, in this case 3, into R2. So his question is, are we wasting space in R2 which can hold 32 bits by only storing a 3, which can be represented in as little as 3 bits. Now keep in mind, so or sorry, 2 bits. So a 3 is that, all right? But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. That is also a 3. So what he's really asking is, are we being wasteful by storing all of this stuff instead of just this? And the answer is, well, in this particular example, we can say, yes, we're wasting memory in that we're not using all these bits, right? You know, we're just padding it with zeros because anything that comes before it doesn't, you know, this is 1 times the 1's place, 1 times the 2's place, 0 times the 4, 0 times the 8, 0 times the 16s, yada, 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 yada. All right, so the idea here is that as a human being, we can look at this and say, well, why wouldn't we store it in the minimum possible footprint? Now, so there's 2 parts to this. One part is, are we wasting memory? We can say, yes, we are wasting memory. But is there an alternative? Okay, I'm going to answer this 2 different ways. We're going to say generally, well, let's go with this way. Yes, we could break up a register into its, well, into 4 or 8 bit, well, let's say 4, 8, or 16 bit segments, which would allow us to store more than one value in them. So an example of this, actually, let me say the words here, then we'll go to a second slide for an example. Or, well, let's just go this route, like this. So now, so what I mean by that is we could decide, I'm going to move this here. So we actually could, I did mention 4 bits, right? Yeah, 4 bits. So let's say that the largest value we actually are going to store is a 7. All right. So we can say example. Let's assume we are only storing values between 0 and 7. Actually, no. 0 and 0 to 9, A to F. The hexadecimal number system, which is 4 bits, right? All right, so let's assume we're only going to store values between 0 and 9 and A through F. So effectively 0 to 15. Right? We could break down a 32-bit register and decide that the first 4 bits hold one number. The next 4 bits hold another number, etc. So let's say we want to hold the 4 values. Let's do 3, 9, 12, and 15. Okay. So we're going to hold 4 individual 4-bit values in a single 32-bit register. Okay, this is kind of what you're asking, right? All right. So the answer is yes, we can do it. But then I'm going to ask a follow-up question is, how do we get the values back out? And actually, even more so, how do I put the values in? Okay. But I'm going to go ahead and we're going to skip the how do we put the values in part, and we're just going to kind of force it. Okay. So I'm going to say at the end of the, so let's just say our register would equal this when we're done. So let's say we're storing it left to right. So this would be 0011. I'll put a little space there to show our individual breakdowns, even though it's not going to have a space, right? So then a 9 is going to be 1s, 2s, 4s, 8s. So that. A 12 will be 4s, 8s, like that. And then a 15 will be that. Okay. So now if I look at that register as a human being, I can say, if I know that I'm actually storing 4 pieces, I'm giving you that information, that there's actually 4 values in here. Or there could be up to 4 values in here, because I'm only using 4 bits per value. All right. And then we talked, I don't remember if it was last class or a couple classes ago, that whole little endian versus big endian thing. So let's just assume our most significant digit is on the right. Doesn't matter. So this would be the first value we're storing, second value we're storing, third value we're storing, fourth value we're storing. All right. Whatever it is. All right. So the answer is, when we have 32 bits of, or I'm sorry, what am I storing here? I'm storing 4, 8, 16 bits. So I can store more values, right? I can store 8 values in here. So let's do a 2, a 1. Yeah, but let me fill out the register just so we're dealing with reality. A 2, 1, a 5, and a 7. So we'll go ahead, and this is 0010, this is 0001, this is 0101, and this is 0111. So that's our full 32 bits. All right. So we're taking up the entirety of this register and actually storing 8 individual 4-bit values. Okay. So I'm kind of giving an extreme example here. Okay. So let's just assume that one way or another, we got those values in there. All right. When we have 32, let's go this route. In real life, if I gave you a container that can hold a fixed amount of stuff, you get to choose how you want to use that space, right? But that choice has consequences. All right. So for instance, let's say that you want to use half a container for shoes and half a container for clothes. Well, you put the shoes in the left half, the clothes in the right half. And when you went in to get it, you would, if you needed shoes, you'd go to the left half of it. If you needed clothes, you'd go to the right half of it. That's allowed, right, in real life. Okay. Similarly, if you wanted to divide it into fourths, maybe you do the upper left-hand corner some stuff, the upper right-hand corner some other stuff. So as human beings, we use our own intelligence to say, oh, well, I'm getting stuff from bucket 3, so I'll just grab from bucket 3. Somehow you had to get yourself to bucket 3. All right. Now, we could also use that bucket to store one type of item. It doesn't have to fill the whole bucket, right? Maybe you get a container at your house for all the, with our electronics, we have a zillion wires and stuff like that, but you only have one wire to begin with. So you got this giant bucket, you throw one wire in it. Big waste of space, but that bucket's for wires. All right. Right now you're only using one. So you'd say, you know what? I'm not utilizing all the space in here, but I'm storing what I need to store. All right. So at that point in time, you would say, well, that's okay, because that's what goes in here. Otherwise, I make it the junk drawer, right, where I can throw almost anything in it. So that's true in real life. The same thing's true in computing. We can say we have 32 bits to work with, and we can say, you know what? I'm only intending to store a single value in here. And chances are, if we're putting something in a register, that's going to be very temporary, right? So we don't need to like go out of our way to like maximize our, you know, the storage. Like, whoa, you know, no, maybe historically when memory was super expensive and we were trying to, you know, pull off the impossible, maybe then we would have cared a little bit more, or at least kind of asked ourselves, can I use this space for anything else right now? You know, with the consequence of then having additional difficulty getting stuff out, possibly. All right. So let's say, so in computing, we can also choose to do this, but we will have the consequence of limiting the, we'll say, magnitude of the values we can store, as well as the complexity of extracting a specific value. Let's steal this. Let's say, okay, we're gonna give a register name to this. This is R0. All right. Let's say we want to extract the 1, that is the 0001 from R0. How would you do this? So you want to get this guy right here. How do you get, so taking kind of what we know right now and then maybe a little of foreshadowing, and this kind of also kicks back to maybe some stuff maybe that you should know from an undergrad degree in it for manipulating binary numbers. But I think we've probably talked about everything we need to talk about in here at some point. You might not know the name of the command, but you know the stuff to do it. I need this guy. So here, ultimately, we want this. Man, Galib, the lights are going out again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Did I get that right? I feel like I missed 27. Set it in my head. How do we make that look like this? Because ultimately, if I read from that value, I get my 1, right? If I read from this register right now, I get my value 1. That's the value of that, right? So how do I take something like this, where I've effectively encoded the register to hold, in this case, 8 individual 4-bit values, nibble size values? That's what a 4-bit value is. We have nibble, we have byte, we have word, we have double word. So what can I do to this collection of bits to get them to ultimately look like this?
it's gonna use dates to differentiate, to extract the one from the other one.
Okay, so we might need to use some bitwise operations. Okay. Well, first of all, let's start one step at a time. How do I get this guy to be at the far right? Well, what has to happen, just as a human being? What has to happen to this bit in order for it to be right here?
It has to be shifted.
Yeah, we got to shift it. We got to shift it 8 bits, right? So first, shift, we'll say right shift 8 bits. So that's the result of right shifting 8 bits. Now, how do we get the rest of this to be zeros? And for this to be preserved? Yeah, okay, it is going to be a bitwise operation. Which bitwise operation? And then you'll see the pattern here. What bitwise operation can I perform on this guy to make it ultimately look like this guy? Let me hit you. How do I make this part be all zeros?
Bitwise and.
Bitwise and against what? So what do I put? What am I bitwising and that stuff against? What's the values I put in that I'm bitwising and? How do I make a 0 a 0? Bitwise and it against the what? Okay, and how do I make a 1 a 0? Bitwise and 0. So if I bitwise and all of that against zeros, I'm guaranteed to get zeros. 0 bitwise and 0 is a 0. 0 bitwise 1 is a 0. Correct? Okay, so I know I'll get my output of, I just copy this one, right? I know if I bitwise and it, I'll get that output. How do I preserve the output there? I'm still doing bitwise and though. So what do I need to put here to preserve whatever these last 4 bits are? I know my actual value is in those 4 bits. I got to make this generic though, so it always works. I want to keep the state of the last 4 bits. What can I put here to guarantee that I keep the state of the last 4 bits? A bitwise and gives me a 0 if I bitwise and it against a what? Or a 1. A bitwise 0, 0 or 1. What about a bitwise 1? It stays a 1 if I bitwise and it against the what?
Right. Against the what? Against the 1.
Against the 1. That do it?
Right.
So now my final answer is 0001. So you right shift by 8 bits and then bitwise and all zeros followed by ones in the last 4. And there's our final value of 1. So that will allow us to extract a particular, if we think of this guy now as an array of numbers. If we want bucket 0, we don't shift it at all. We want bucket 1, we shift it by 4. You want bucket 2, you shift it by 8. You want bucket 3, you shift it by 12, so on and so forth. And if you're storing 8-bit values instead of 4-bit values, you jump by 8s. Okay? So you can choose to use those 32 bits however you want to use them. But ultimately, if you're going to say, well, I know the values I'm storing in there are smaller. And I also know that I want to store lots of values, because you're always playing the game over against, well, I'm limited with the number of unique values I can store by the number of registers that there are, as well as the size of those registers and the size of the data that I'm storing. I can play the game, right? I can shove multiple values into a single register as long as I say, I know I actually have 2 things stored in there. And when I want the first thing, I need to bitwise and it by everything by zeros followed by 1s to preserve. If I want the second thing, I need to do a shift first and then do the bitwise and thing. Make sense? So you can extract values, but that's a choice. The human being gets to decide, I'm going to use this storage location in a certain way, and that comes with the consequence of extracting my value is going to be a little bit more difficult. Whereas in the case here, we were able to say, let's see, where were we back here? You know, this is fine. I'm just storing a 3. Who cares if I'm doing it in 32 bits? I don't really have a desire right now to, and I'm just moving it around and stuff. So you say, why make my life more complicated when I just need to temporarily store this 3 and move it across? Yeah, one's not better or worse than the other. It just comes with a consequence. But it's an important lesson for us because it separates this idea of magnitude versus bit space, which I think is an important thing in computer architecture for us to consider. Magnitude versus bit space. So magnitude is the actual value we are storing. Bit space is the footprint. Let's call this, actually, let's say the available memory in which we have to work with to store value with the S, little parentheses S thing at the end. We can decide how much we want to shove in there, right? But bit space tells us the size of the box. How big is the box that we have to store our stuff in? Make sense? We can use that box in whatever way we want. But how things are stored dictates how we get things out of the box. Make sense? So this idea of bit space, having a 32-bit register, doesn't necessarily, I mean, a 32-bit register does dictate the maximum size single value you can store in there. So that's an unsigned 2 to the 32nd power or a signed 2 to the 31st power, plus or minus-ish. There's an extra 1 on the negative side. All right, so it does, so if you have a maximum size container in real life, you are limited by that size of that container with what you can put in there. You can't go buy a container from Home Depot that, you know, is kind of big enough to maybe hold 10 pairs of shoes and just decide I'm going to put a car in there. Won't fit. Okay, so you are going to be limited by the maximum amount of bit space you have. But if you don't need to use that whole bit space, take a garage. You have a garage, right? It's built for holding a car. In fact, sometimes you have 2-car garages built for holding 2 cars, right? But let's say if you only have 1 car, you say, well, I'm going to put my car in there, but I'm also going to put some other stuff in there. Make sense? So now I have multiple stuffs in my, you know, in my garage. I've organized it in a certain way, but you might have a situation where if you want to back the car out, you got to move some stuff around. Or you need to put more stuff in there, you're going to back the car out first, you know, that kind of stuff. So it comes with those consequences. So the thing I want us to walk away from this with is this idea that it's not dissimilar to real life, right? Bit space, the size of the box, is the same as we deal with in real space. We can use that box however we want, but how we take things out or put things in has a consequence. That makes sense? Where magnitude is how big a value is. Magnitude's the size of that car or the size of the snowmobile, you know, whatever it is, whatever you're storing in whatever you're storing in the garage in that case. All right. So make sure you don't necessarily put a register up on a pedestal and say registers are made for holding flat values. Because a register, that box, could be used for storing things in interesting ways. Your knowledge of how you put stuff in there will dictate how you get stuff out of there. Okay, that makes some sense? That allows us to be problem solvers as computer scientists, you know, because we could say, look, we just kind of put a limitation on ourselves. We can say, you know, I have 4 registers. Let's take some very simplified architecture. I have 4 registers. I need to hold 5 values. Ruh-roh. Okay, and we're going to throw memory out the window. We can't use system memory, right? We're going to talk about stacks and stuff some today. You know, so you have a couple of other options, but we're keeping this super simple. Okay, I got 4 registers. The limitation of how I remember crap in this architecture is I have 4 registers and I got to store 5 things. Well, I can't unless I get creative, right? Now, we just saw that I potentially could store all 5 of those things in one of those registers if those 5 things meet a certain criteria, right? If they're not too large. But I got some flexibility now. I can kind of look at this and I'm solving the problem. Okay, I got 5 32-bit, I have 4 32-bit registers. I have 5 values. As long as they're not all 32-bit values, if they're all, you know, assigned to, you know, 2 billion, you know, if all the values are, you know, assigned 32-bit number is negative 32 billion to, negative 2.1 billion to positive 2.1 billion. So if I'm trying to store the number 2 billion 5 times, let's say it's 2 billion, 2 billion and 1, 2 billion and 2, 2 billion and 3, 2 billion and 4. Okay. Now I got a problem. All right. I don't have enough boxes. Can't break them down because each of those, I'm going to need almost the entirety of each of those boxes to hold each of those numbers. And I only got 4 of them. I got 5 numbers. Can't solve that problem with this architecture. Out the window. I got to store 5 values. I got 4 buckets. Huh? No. Right, you can't. Right, yeah, you can't. So we're playing the game. You know, so you can't accomplish the impossible, but if you know that all your values are less than 1 million, let's say, you can say, oh, now I got a little wiggle room. You know, let's make these 4 registers last type thing. Kind of see where we're going with this? All right, but so it's an important thing in terms of problem solving at the architecture level is the architecture does not dictate how we store information. Well, other than it needs to be in bits, 0s and 1s. It dictates the maximum size of the box. How you use that box is up to you, and it's giving you some magic tricks for working with, with that box. Okay, I know a little long-winded, but good. It's a good question and it's an important question. All right, any questions about what we just talked about there? Okay, so otherwise, if you kind of go back to the code here, how would you accomplish this? We won't actually go and write it because I want to talk about some other things, but it should be pretty straightforward, right? Got 3 variables, load them into some registers, and then use some additional registers to start doing some swapping until ultimately you have your numbers reversed. Okay. Okay. Where you would use some stores to kind of throw things back in memory and to overwrite what the values point to. Okay. So should have been fairly straightforward given that you have a nice, good size collection of registers to work with for only dealing with 3 values. Plus we had system memory. Okay. Now, a couple people asked about using stacks to accomplish this. So, here's the reality, and let me just give you my interpretation of this, where those people were going. I'm assuming they were working together, which is fine. It's not a problem. When you have a problem to solve, typically I'm asking you to solve it in terms of the stuff we've covered. Secondarily, and probably more importantly, I want you to solve it with your own brain. Don't go and search for the answer. Well, don't go and search other places for the answer. Search your brain for the answer. It's not a memorization thing. It's here's the tools I have in front of me. We solve problems using the tools we have available to us. Here's the tools I have available to me. How can I solve this problem in terms of that? So, when you look at this and this example has you storing 2 variables, and then it has you overwriting one of them, storing the value of one of them in the other place. So this gives you all the tools you need to solve this problem, right? So the fact that you might even think about going outside and saying, well, maybe we can use something we haven't discussed yet. Well, the answer is probably yes. There's probably are some more magic tricks that might allow you to do some things like this more easily, but you're doing yourself a disservice by going and searching for a solution outside of your brain, because you're doing homework is where you're putting in those reps to start critically thinking through this stuff. All right. So, and that doesn't just go for my classes, it goes for any classes, because ultimately the reason you're in school is to learn, right? I get paid either way. And if you want to go find your answer on Google or something like that, I mean, that's fine. But you're only hurting yourself there, because I mean, ultimately, especially when we're dealing with architecture, you take our conversation so far today, it's been a very technical conversation, but hopefully in the end, when we came out the other side, you realize this isn't as complicated as I maybe thought it was. It just seems scary because I'm dealing with zeros and ones. It's an uncomfortable numbering system for us, right? But once you kind of get past that and you realize, oh, it's just numbers. And if I had a box in front of me, I could organize that box to store 4 different things. That's an easy thing for a human being to do. It's pretty easy to do in the computer too. You just have to do it in terms of the tools that you're provided. Okay. So let's see, we did that. No, I do want to talk about program counter, because I haven't talked about program counter yet. So this is actually a difference. Does it talk about it up here? Yeah, it does. So there's a difference between, if you go back, and some of you did write about it in your paper when we were comparing Intel architecture versus ARM architecture, is we have this thing called the program counter. And let me go ahead and actually just give us a kind of a precursor slide. Program counter PC. So we're going to say one way or another, this guy holds the information regarding what the CPU will eat next. Okay. you probably caught on by now. I like to use some non-technical terms to kind of demystify some of this stuff. Because again, it's not that hard as long as you keep yourself from being scared witless constantly, right? All right, so, we've talked about the CPUs kind of being like Pac-Man, it eats stuff. Well, somewhere in the CPU architecture, we need to store, hey, what's Pac-Man eating next? Okay, or ish, something related to that. Okay, so that's the job of the program counter. So the program counter, let's actually write it as PC, holds the necessary information to figure this out. In Intel, it directly holds the next instruction. I'm going to say the location of the next instruction. In ARM, it indirectly holds the location of the next instruction. ARM jumps ahead 8 bits. All right? Yeah, 8 bits, 2 bytes, which is the size of exactly 2 ARM instructions. So an ARM instruction is 4 bits, right? So if an ARM instruction is 4 bits, how many unique ARM instructions are there? If an ARM instruction is 4 bits, if an ARM instruction is 4 bits, how many unique ARM instructions are there? Well, tell me all the values you can store in 4 bits. We actually talked about this today already. So again, this is keeping us in the swimming pool of dealing with bits, and they're scary. Okay, we got 4 bits. Can I hold the number 0 in 4 bits? Can I hold a 1? Can I hold a 7? 4 bits? What's the biggest value I can store in 4 bits? 15. 1111. That's an F, right? 15. So how many unique values are there in 4 bits? How many unique ways can I write 4 zeros and 1s? That's what I'm really asking here. 16 different ways, right? So that means that if we have 4 bits to store an ARM instruction, that means I have 16 unique instructions. Make sense? All right. So ARM is a reduced instruction set thing. Now, with that in mind, as ARM has gotten more and more complex, you imagine that maybe we have more than 16 instructions. So we have to have ways of, again, using bit space to use those 16 unique instructions as perhaps information. Maybe we have a type of instruction, and then within a single type of instruction, we can have 16 unique instructions. Okay. Rather than saying the entire architecture has 16 unique instructions, because then we start running out of magic tricks. Okay. So we can use a couple different registers potentially to keep track of the unique things. Not important to what we're talking about right now, but just because we say that a unique instruction is, and it is, I want to make sure it's 4 bits before I go. The same example I'm using is true. I just want to make sure I'm advertising it correctly. I'm pretty sure it's 4 bits. Yeah, it's 4 bits. Actually, no, that's 4 bytes. Yeah, so let me go back. this is 8 bytes or 64 bits, which is the exact size of 2 ARM instructions. So if an ARM instruction is 4 bytes, that's a 32-bit instruction, which gives me a maximum number of instructions of 4.2 billion. Okay, which we probably haven't used that, but the previous example was still true, right? The previous example still goes down our path of saying, hey, if I could only hold 16 unique instructions and I need more than that, I got to come up with a trick. I got to use a different register to maybe say, well, instructions of type 0, we can have 16. Instructions of type 1, I can have 16. Instructions of type 2, I can have 16, so on and so forth. So we can play the game to do it. So ARM jumps ahead 8 bytes, 64 bits, which is the size of exactly 2 ARM instructions. So if an ARM instruction is 4 bytes big, how many unique ARM instructions are there? That is 2 to the 32nd power, which is roughly 4.2 billion. 2 to the 32nd is 4.294 billion. That guy. All right. So that's the number of unique ARM instructions we could have. We don't have that many. Okay. But we could. We could have that many. All right. They've decided, since all their registers are 32-bit registers, and we're probably going to store a single instruction in a register, we might as well use up the space, because maybe we're not going to do this shifting and bitwise anding stuff with the instructions. Maybe we're just kind of going to throw that to the side, because we'll give you enough buckets. But in any case, the difference here between ARM and Intel is that Intel stores the exact location of the next instruction, where ARM gives you the location of really the next 3 instructions, because it's giving you 2 instructions in the future, which you can then subtract 4 bytes from to get to the 1 instruction in the future, and 8 bytes from to get you to the current instruction. Now, you can still go the other direction with Intel, right? You could say, well, if the current instruction is here, the next instruction will be plus 4 bytes. The next instruction will be plus 4 bytes. And we can say that that's probably mostly true. But something else we're going to talk about here is, we might not get to it today, but whatever. So we're going to talk about branch instructions, where you could, program counters typically keeping track of what line of code are you on. Okay. If you know the line of code 2 things in the future, that doesn't necessarily mean that that's where you'll actually be in 2 instructions, because you might hit effectively an if statement, which takes you to another place in the code. Make sense? So really what you're doing is you're giving yourself the advantage, possibly, of preloading what is likely. We're just going to use the word likely. It might not even be statistically proven that it's likely. But we can say, look, I got some memory to work with here. I'm going to go ahead and say, I know the current instruction is whatever ARM's program counter is minus 8 bytes. I think the next instruction will be whatever the program counter is minus 4 bytes. And I think the instruction after that will be whatever the program counter is, period, not minus any bytes. I could preload those instructions, kind of an idea of pipelining at the on the actual CPU, rather than using L1, L2, L3 cache and system memory. I could preload in the event that the moons align, and those are the next 2 instructions. Because not every instruction in our code is an if statement or is a call to a function. Many of them are just, hey, move some stuff, right? Okay, so potentially we could see a world in which you could increase your execution speed by using, in this case, 64 bits of memory, an extra 2 times 32 bits to store the next 2 instructions so that they're kind of just ready to go when I need them. They're already in a register. I can just zip them over if that's the next one to actually look at. And if that's the case, I could pick up speed. It's a potentially an optimization.
So that's if I know the code or if I wrote the code. Because
Well, neither. I mean,
if
let's see.
I'm just directing the PC, the program counter without knowing the code, then I'm just assuming the unknown. I'm telling it to get the other 2 instructions that I don't know.
The programmer does not set the program counter. The program counter keeps track. It starts at line 0, goes to line 1, goes to line 2. You wrote the program. Program counter keeps track of what line it's currently on. Okay? But if you wrote a program that had 5 lines in it, the program counter would start at line 3 in ARM and then subtract 8 bytes to get you to the first instruction. But then you could preload line 2 and line 3 of what you wrote in hopes that those are the next instructions and I already have them kind of halfway to Pac-Man's mouth. Make sense? Okay, so there's some optimization there. Not to say you couldn't do the same thing on Intel, right? Intel, you could say, well, I'm just going to guess forward and say, well, I'll go ahead and load the next instruction, which is the program counter plus 4 bytes into a register, and then I'll load into another register the program counter plus 8 bytes. So it's not like one is better or worse than the other. It's just, it's an approach. Let's see what if they have any commentary on it that is more interesting than what I just said. In case you forgot why the effective PC is located 2 instructions ahead of the current one is described, blah, blah, blah. PC stores the address of the current instruction plus 8 2 more instructions in ARM state, and the current instruction plus 4 2 thumb instructions. I mentioned thumb earlier, even though we're not talking about it. Thumb is just a lower power to ARM. This is different from x86, where PC always points to the next instruction to be executed. All right, unimportant. So it's 2 approaches to the same thing, where there might be some optimizations that could be taken advantage of, something like that. All right, so now let's talk about offsets. So when we talk about memory offsets, we're going to say a go-to move in computing is to start with the base address of something, where the base address is where that something starts. Then let's say walk memory by some offset, where an offset is the number of steps. I'm going to say n size steps you take from the base address to ultimately get to the value you want, where n is the size of the data type being stored at that memory location. For example, if we are storing 8-bit chars, we would take 1 byte size steps. If we are storing 32-bit ints, we would take 4 byte size steps. All right, makes sense. The purpose of memory offsets. So kind of a normal cadence. So this is similar to what we talked about earlier today where, you know, hey, we can use memory in different ways if we just want to get creative. So another interesting thing here is we can say, look, it's going to be pretty common since I have this. I'm going to start another slide here. Why do we do this? So we could say it's pretty common since I have these different memory resources. All right, so I have different memory resources like registers, cache, system memory, etc. System memory specifically is commonly used to store data that will be needed soon. Why is that? Why is system memory commonly used to store data that we're going to need soon? Data that we're going to need immediately, we probably want stored in a register. But data that we need soon, we store in system memory. Why is that? Well, data that we're gonna be using right now, very next Pac-Man byte, is going to be in a register. It's going to get one way or another. It's gotten into a register. But data that we might need soon, data that should be on hand so we can use it very soon, we put inside system memory. Why is that? What are the advantages and disadvantages of system memory? What are the advantages of system memory?
Loads quickly.
Okay. It loads quickly relative to what?
Oh, I
What
mean,
loads slower than system memory?
lower than system memory. I mean, like if we are using multiple applications, then
No, just what other device loads more slowly than system memory? Hard drive. So hard drive loads slower than system memory. What things load faster than system memory? Everything
Registers.
else? Yeah, all the caches, the registers, all those are faster. So we can't just blanketly say, well, system memory is fast. Okay, we can say system memory is relatively fast compared to the hard drive. And the other advantages? Yeah. Why don't we just make the whole computer out of registers? If registers are the fastest, why have L1, L2, L3 cache, system memory, hard drives? Why doesn't everything just operate off of registers? Our whole hard drive is just registers. Super fast, right? That would be awesome. Why don't we do that? Yeah, what kind of limitation? Well, is it really a size? I mean, registers don't seem that big. They should, you know, they get a bunch of them fit inside that little processor. And then that processor usually has multiple cores. Each of those cores has their own set of registers. So if we took something the size of like a mini fridge, couldn't we fit a whole bunch of registers in there and just say that's a big old hard drive? Yeah, probably. Why don't we do that? Okay, maybe. I mean, certainly size is a consideration, right? But some of these places, we got server rooms and stuff like that. They don't care. They'll, you know, if they want it super, super fast. Why don't we have our 2 terabyte hard drive? made up of registers. If a register holds 32 bits, how many registers would we need to hold 32 or hold 2 terabytes? How many registers would we need to hold 2 terabytes? How many 32-bit registers? Everybody take a couple minutes and try to do that math. Yeah, you can do a calculator. Use a calculator. How many 32-bit registers would we need to hold 2 terabytes of data?
In the vicinity of 67,000.
Okay. So, well, first of all, we need to find out, well, how many bytes are in 2 terabytes. So it's 2 times 1024 is gigabytes times 1024 is megabytes times 1024 is kilobytes times 1024 is bytes divided by 4. So we need this many.
Well, I think you, yeah.
No, that's right. 32 bits is 4 bytes.
No, I'm not, okay, no problem. I'm not talking about the 4, I'm talking about between brackets.
Why? Multiplication, division, left to right. It'll be the same value. So that is equal to, oh, I need to get a drink here. $5.49. Oh. Jeez. That many. 549,755,813. I'm sorry, 755,813,888. A lot. A lot of registers. 549.7 billion registers to hold a 2 terabyte hard drive. How much do you think one register costs? Who knows? But they must be, since it's the fastest memory, they must be pretty expensive. Let's just use $1 as our, you know, heck, let's look it up real quick. How much does a modern hardware register cost per byte? No, that's like giving a.
I think it's 2 cents per GB per
That's
gigabyte.
for that's for hard drives. Just hoping to get. I just wanted to get a number so you can really see the reality of it. I'm just going to operate off of my guess. I'm going to say, just to keep our number simple, even if it's a lot less, it still shows the problem. If we assume a register costs $1, which would not surprise me. It seems like a reasonable cost. I mean, you think about, you know, the how computers or processors are put together. $1 I don't think seems ridiculous for the cost of a register. That means that our 2 terabyte hard drive would cost $549.7 billion. So warm up that credit card. Right? get that.
I have that calculator too.
Get that guy greased up, ready to go. All right, so that's why we don't use those guys, right? So advantage of system memory is they're relatively fast compared to the hard drive. They are relatively, it is relatively large compared to registers and caches. So it is kind of the right balance between speed and size, where we don't have to manage the number of things we are able to store very often. Does that make sense? That's why system memory is kind of a nice place. You know, it's still pretty fast. Not nearly as fast as a register, but pretty fast. Way faster than hard drives, even solid state hard drives. All right. And it's a pretty good size. You know, even if, you know, so a modern day computer, we might say for a technology person, we should have at least 8 gigabytes of memory. Okay, so 8 gigabytes of memory, that's a lot of 32-bit values we might hold, right? So 8 gigabytes. So 8 times 1024 is megabytes, times 1024 is kilobytes, times 1024 is bytes, divided by 4, that's 2.1 billion, right? And this is 8 gigabytes times 1024 gets me megabytes, times 1024 gets me kilobytes, times 1024 gets me bytes. That's the number of bytes I can store. Divided by 4 gets me the number of 32-bit 4-byte integers. So I can store 2.1 billion integers in 8 gigabytes of system memory. So that's 2.1 billion values that would fit into a single hardware register. Now, don't you think that most of our computer programs aren't going to be that reliant on storing that many elements? Even if we have 5, 6, 7 computer programs running on our computer at once, do we feel like we're in a pretty comfortable place with 2.1 billion options? Now, not everything's the size of an integer. Some things are larger. We have, you know, all the pieces of information associated with maybe an image that's loaded into memory. But if we know we're dealing with 2.1 billion integer size containers, we imagine that's a currency that's going to last us for a good amount of time, right? So we'll say 8 gigabytes is fine. You want to double that? No problem. Go to 16, so on and so forth. All right. So this is all related to what we've talked about today with these things have footprints, right? So why do we have different resources like registers, blah, blah, blah. System memory is commonly used to store data that will be needed soon. Why? Because it's relatively fast and relatively big. Okay, those two pieces of information. We only store stuff what goes in the registers. We only store things that will be used immediately inside of a register. And we put things that will be stored soon in system memory. We then provide mechanisms for bringing, let's see, just for moving data between registers and system memory. With some nice magic tricks involving L1, L2, L3 cache in some cases. So we can call cache memory as kind of like the, you know, the sneaky way of getting something kind of halfway to your register. You know, it's like if I know I'm going to need a value very, very soon, but not immediately, if I can find a way to get that into like L1 or L2 cache, then it's already kind of made half the trip, right? It's half the way to the CPU, half the way to the register. I've picked up some time. All right. Questions about any of that stuff? So just out of curiosity, I won't give an official homework assignment for Wednesday, but look into to see if you can find the cost per bit or byte of a modern day hardware register. That way we can put a real value to it. And then we'll finish up this conversation with stacks and stuff. So we didn't quite get where I was thinking we were going today, but we got a lot of good stuff. So I think we're fine. I just not ready for the next assignment. I assume nobody's complaining I'm not giving you assignment for Wednesday? No complaints, we're good? All right. Questions, comments, concerns, bribes? All right, I will see everybody Wednesday morning.